Okay. Okay, so we are doing the Lacunary theorem, right? So that's this thing where you have so given a non-negative, non-increasing sequence that we're going to call a sub n, then summation a sub n converges if and only if the Lacunary, what I call the Lacunary series converges. You guys arrived too late to hear about my near-death experiences. Anyway, I'm joking. Well, kind of joking. Okay. This thing converges if and only if the Lacunary, what I'm calling the Lacunary series converges. Okay. And the proof is kind of the following. So you make the following observation. Say, look, if I have the sequence A1, so it's basically you partition things diagonally. So A1, A2, A4, A4, A8, oops, A8, 16, etc., right? Right. So right. So you say, well, look, if I'm just going to write it, no. So if we look at, the sequence is non-increasing, right? So basically the terms from here on in are less than A2, right? There's just one term. But from here on, these terms are less than A4, less than or equal to A4. These terms are less than A8, and they're like that, right? So things are decreasing, right? The Lacunary sequence is, of course, A1 plus 2A2 plus 4A4 plus 8A8 plus etc. Right? So you see that if you're looking at your original sum, then 2A2 is going to dominate this block, right? If you look at the head of this what I'm calling a dyadic block. So what I mean by dyadic is like powers of 2, right? So this is a block of length 2 to the 0, block of length 2 to the 1, block of length 2 to the 2, block of length 2 to the 3, etc. So you partition things diagonally. And you say, well, look, if we look at the heads of these blocks, well, the head is the biggest piece, right? So if I take 2A2, that dominates, that 2A2 is bigger than the sum of the terms in the block, right? 4A4 is going to dominate this block, right? 8A8 is going to dominate this block, and so on and so forth, right? Right, so the observation is that, the first observation is that if n is less than 2 to the k, then S of n is dominated by T sub k. So where S of n is the partial sum of the AIs, right? And T sub k is the partial sum up to nth term. So we have like this, A1 to AN, and T sub k is the partial sums of the Lacunary sequence, 2 to A2 plus 2 to the k, A sub 2 to the k. Okay, so here's the first observation, right? That if n is less than 2 to the k, then the sum of, right, if n is something, let's say that this is 2 to the k, okay? Right? If you have some n that sums, terms less than the 2 to the, before the 2 to the kth term, well, that thing is definitely smaller than the sum of the Lacunary terms up to the 2 to the kth term, right? Because of this observation of the head being the biggest, right? Right, because the head, this Lacunary thing is going to dominate this entire sum here, right? Right. So anyway, so do you guys see what I mean? Right. Okay. So right. So the S sub n's are smaller than the T sub k's, right? So the what you can observe is that since S sub n is smaller than T sub k, if the S sub n diverge, right? If the S sub n are unbounded, right? In other words, the original sequence diverges, i.e. this thing diverges, then certainly the T sub k are going to be unbounded. And the original, the Lacunary sequence diverges. Right? Right? Because certainly, right, if these guys diverge, these guys, the smaller guys diverge, if the smaller guys are unbounded, well, the bigger guys are certainly going to be unbounded. Okay. So that's sort of like noticing that the heads are the biggest in each dyadic block. That's the strategy. In each dyadic block, the heads are biggest. Okay, so that's part one, right? Like if these guys diverge, then these guys diverge. Okay, now we're going to go backwards. Okay, part two is you look at the tail terms. You say, well, look, we're gonna split them this way. Okay, we'll split them with the dyadic terms as the tails. Okay, we'll go instead of taking these powers of 2 guys as the heads, we'll take them as the tails. Okay, so we're going to partition things like this. Here's the first block, here's the second block, here's the third block, here's the fourth block, here's the fifth block, and so on and so forth. Right? Same sort of thing happens, of course, right? The tail is the smallest, right? Because these are non-increasing sequences. Right? So you notice that the tail is the smallest, and so well, so what do you notice? That this thing here, this block here is bigger than 2A4, right? This block here is bigger than 4A8. This block here is bigger than 8A16, and so on and so forth. Right? This block here is bigger than or equal to A2. Of course, it's equal to A2. This block here, we're going to say it's bigger than or equal to 1/2 of A1. Okay. Right. And so what you see is that, so now, second part of the strategy is like, in the new dyadic blocks, the tail is the smallest. Right? And so what does that have? That says that as long as n is bigger than 2 to the k, then S sub n is bigger than or equal to t sub k, 1/2 t sub k. Right? Because this thing here that we have here is 1/2 t sub k. Right? When we sum all these things together, t sub k, remember, was A1 plus 2A2 plus 4A4 plus et cetera, right? Up until 2 to the k, a sub 2 to the k. But what we have here is 1/2 of that. Okay, but that's still okay, right? In any case, what we get is S of n is bigger than 1/2 of t sub k, right? And now we've got the same argument, right? If these guys, if the t sub k's are unbounded, well, then the S of n's are going to be unbounded, right? So same sort of thing, right? If these guys diverge, then these guys diverge, right? So if these guys diverge, those guys diverge. If those guys diverge, those guys diverge, right? So they either both converge or they both diverge. Okay. But really the idea is, there's one idea, which is, look, your sequence is decreasing, right? Your sequence is decreasing. So if we divide it into dyadic blocks in these two different ways, where the terms are heads or the terms are tails, then we can compare the partial sums. Okay, so that gives us, yeah, it's kind of a simple, right? This is a pretty simple observation, right? This observation, look, this is the big guy, so twice this guy dominates the block. This is the big guy, so 4 times this guy. Yeah, that's a very simple observation, right? That simple observation gives us this handy tool, the Lacunary series, Lacunary test. Okay, so, okay? Great. Okay. Anybody still copying? No. Okay, so we're going to use the Lacunary test. Well, we're going to combine the Lacunary test with so-called geometric series, yeah, with the geometric series to get some other tests. So, yeah. Okay. So here's the your old friend, the geometric series, right? So summation x to the n from 0 to infinity, right? So geometric series. Anybody remember about this? Like, it's maybe your distant past, geometric series. When does this converge? When does this diverge?
This converges if x is less than 1.
Say one more time.
X is between 1 and x is between 0 and 1.
If x is between 0 and 1, yeah, it will converge. Yeah. Yeah. So this thing converges, in fact, to a particular number, 1 over 1 minus x, if and only if x is kind of small enough, right? So think, if x is 1, what's going to happen? We're just going to get 1 plus 1 plus 1 plus 1. That's going to diverge. What about if x is negative 1? If x is negative 1, you're going to have, excuse me, 1 plus negative 1 plus 1 plus negative 1 plus 1 plus negative 1 plus 1 plus negative 1, right? The partial sums are going to just bounce back and forth, right? So you're always going to be adding 1, subtracting 1, adding 1, subtracting 1, right? So that's going to diverge also, right? It turns out that as long as you're between 1 and negative 1, then it converges. Okay, so it converges if and only if the absolute value is less than 1, and it converges to this value of 1 over 1 minus x. Okay, so the proof is to consider the partial sum series, partial sum sequence. So let S of n denote 1 plus x plus x to the n. Maybe? Yeah, let's do that. Plus x to the n. Okay. Did anybody remember the trick to this? It's kind of a cute trick. No? No? Okay, so the trick is, you're trying to figure out what S sub n is, okay? And you think, well, look, if I multiply S sub n by x, well, that's going to give me this thing times x. Well, that's x plus x to the n plus x to the n plus 1, right? Right? So now if I subtract the lower guy from the upper guy, right, then I'm going to get 1 minus x times S sub n, right? So you get S sub n minus x S sub n, right? That's that. And then you have a lot of cancellation that occurs, and you get this. Right? That gives us a formula for S sub n, right? S sub n is going to be 1 minus x to the n plus 1 over 1 minus x. Right, so this is kind of handy. Like, you know, if somebody says, what's 1 plus 3 squared plus 3 cubed plus 3 to the 1,987, right? Then you've got a very quick formula for it, right? You say, well, that's just going to be, 1 minus 3 to the 1988 over negative 2. I think I remember seeing something like this in math club in high school, right? Where they give you, like, you've got 30 minutes to solve 5 problems or something. And yeah, I'm pretty sure I saw something like this. And had no idea how to do it. Okay, everybody all right so far? Right, simple, right? So we can, here's the partial sum sequence. Turns out that there's a kind of very easy way of getting, there's a trick you can apply to get this formula for the partial sum. Right? Okay. So, right. So, right. It's pretty clear that so observe that this thing definitely diverges for x equals plus or minus 1, or x bigger than 1, or x smaller than negative 1. Right? Right? Because if x is bigger than 1, your nth term is going to go to infinity. Right? If x in absolute value is bigger than 1, then the size is going to go to infinity, right? And so by the divergence test, you know that this cannot converge, right? So, and also so, and if x is bigger than 1, then the absolute value goes to infinity. So you have divergence. Now, if the absolute value of x is less than 1, then look at the partial sum sequence, right? And I probably could have done this all at the same time. I don't really have to use the divergence test. I can just say, look at this thing, look at the partial sum sequence. Let me do that, sorry. So, consider the partial sum sequence. If absolute value of x is smaller than 1, then what's going to happen? What happens to the partial sum sequence? Absolute value of x is smaller than 1, so what happens to this term? Goes to 0, right? This term goes to 0, right? And then so the partial sum sequence converges to 1 over 1 minus x, right? And if absolute value of x is greater than 1, then clearly the partial sum sequence diverges, right? Because this term is going to become huge, right? If it's a negative number, it's going to bounce back and forth between bigger and bigger negative and positive numbers. If it's a positive number, it's just going to become a huge positive number. And so this thing's going to diverge. Is that okay? Yeah, questions? Okay. Okay, so that gives us your old friend, the geometric series, and you probably saw this proved back in Calc 2. Do you guys see it proved back in Calc 2? I hope so. It's not that hard. Right, you can use the divergence test plus this simple algebraic trick. Okay, so now from this plus the Lacunary series, so now we add in the Lacunary test. And we can get such things as the p-test. Converges if and only if p is bigger than 1. Okay, so you guys also saw this back in Calc 2, right? Do you remember how you did it in Calc 2? How you proved it in Calc 2? No. You probably used something called the integral test. You changed this thing into an integral. You saw that the integrals diverged or converged by using integration, but we haven't introduced integration yet, so we're going to use the Lacunary test. So the proof is as follows. You say, well, look, if p is less than 0, p is less than or equal to 0, right? If p is equal to 0, we're just summing ones again, right? If p is less than 0, then you've got a negative power here. So you've got 1 over n to a negative power, right? That's the same thing as n to some positive power, right? And so you're summing terms, you're letting n go from 0 to infinity. You're taking, maybe I should say from 1 to infinity. You're taking terms that just get bigger and bigger, right? And so, so just that purchase. So that's pretty straightforward. So assume p is bigger than 0. Okay. So if p is bigger than 0, well then this is a decreasing sequence, right? This becomes a decreasing. These guys have become decreasing, and so we can apply the Lacunary test to it. Okay, so now apply the Lacunary test. Let me see if you can apply the Lacunary test. So what do we need to compare this with? Take 1 second and write down, so this thing converges if and only if, right, by the Lacunary test. Okay, so what is it? What do we need to compare it against? Anybody want to say? Charlotte?
2 to the k a sub 2 to the k.
a sub 2 to the k, where this is our a, this is a sub n, right? This is a sub n, so what do we need to compare to, what do we need to do? We need to take 2 to the kp, right? We need to take 2 to the k times the 2 to the k term, right? The 2 to the k term here is 1 over 2 to the k to the p, right, which is 2 to the kp. Okay. Okay. So that converges if and only if this thing converges, right? Well, you can use your rusty old knowledge of exponents and say, well, okay, this is the same thing as 2 to the k times 1 minus p. I hope. Right? Which I can rewrite. Same thing as 2 to the 1 minus p to the k. Right? As k goes from 0 to infinity. Okay, but now, what do we have here? What is this? Something to the kth power as k goes from 1 to infinity, right? Well, that's a geometric series, right? So for this to converge, we need this thing to be smaller than 1, right? In other words, we need p to be bigger than 1, right? So this thing which converges, which is a geometric series, and thus converges if and only if p is bigger than 1, right? Right, so that we need 2 to the 1 minus p to be smaller than 1, which is the same thing as we need 1 minus p to be smaller than 0. Right. 2 to the 0 would be 1, and then 2 to something smaller than 0 is going to give us something smaller than 1. Okay, so this is good, right? And this gives us, that the information about the harmonic series that we mentioned earlier, right? If you take summation 1 over n, well, that's p equals 1. So we have divergence, right? So the harmonic series diverges, right? So in terms of like application, right? Summation 1 over n diverges. Right, because it's 1 over n to the 1, right? Your p equals 1, so you have divergence, right? Summation 1 over n squared converges, right? Summation, to make it a bit finer, summation 1.000000000001 converges, right? Actually, let me write this like this. N to the 1 times n to the 0.00000001. Okay. So if you just speed up the base a little bit, right? Right. If you're looking at the bottom, right, n squared is faster than n to the 1. Right. So n squared is growing faster. That means these guys are shrinking faster. These terms are shrinking faster, right? And so you say, look, this thing shrinks fast enough that this thing will converge. This thing doesn't shrink fast enough, so it doesn't converge, right? You notice that, if you multiply this guy by just a very slow term here, it'll still converge. Okay. That leads us to the next theorem, which is about what if you look at things like 1 over n log n. Okay. What if you look at 1 over n log n to the p? Okay. I don't know if you learned this back when you were doing calculus, but hopefully you did. You learned that if you have log n over n, then when you take the limit of that, that actually goes to 0. That log is slower than n. Log loses out to n. Okay. In fact, log is slower than any positive power. Okay. So like, no matter how slow you go here, log is even slower than that. Okay. So, right, so you may be wondering, if you remembered that fact, you would be thinking, well, we multiplied by this guy and it converged. What if we multiplied by something even slower? Would it still converge? You know, multiplied by log, would it still converge? And so that's what leads to this. That's what motivates this next example. Okay. So it turns out that this thing converges if and only if, again, p is bigger than 1. Okay, so once we have that, we'll be able to say, for example, that 1 over n log n actually diverges. Okay, so when you multiply, this guy diverges, and you might think, well, we multiplied by this, and that was enough to make it converge. What if we multiplied by log n? It's not enough. Log n is too slow. Right? Log n is, of course, the inverse to the exponential function. Right? Right? The inverse to the exponential function. The exponential function, I hope you know, is like a very fast-growing function. Right? The inverse is going to be a super slow-growing function. Which means put money in the bank now while you're young, because it will grow exponentially. I always tell the same story at this point, which is when I was in my 20s, I always calculated like doubling times. Like I could spend this $10 now, but if I put it in the bank, it'll go through probably like 5 or 6 doublings. So it'll be multiplied by 32 or 64. By the time I retire, it'll turn into like $640. Right? So do I want this $10 thing now, or do I want to have $640 later? Like, I'm not going to spend the $10. When I got married, my dad said, you cannot continue saving money as you have been, because that will just make your life miserable for your wife. But anyway, yeah, don't think too much about doubling times. Now that I'm older and the money will not double more than once or twice, I feel a little bit more free to spend it. Okay, but yeah, when you're young, if you think about it, things will go through multiple doublings. So just savor them. And don't get credit card debt, because that's the opposite, right? Right? That has a even faster doubling time than your investments, right? And so that's like the opposite. That's the opposite. Credit card debt is the worst, right? Because it's exponential growth, right? Exponential growth, roughly speaking. Okay. So again, we have this. We've got a decreasing positive sequence, so we can apply the Lacunary test. Right, so we apply Lacunary test. Right, this guy converges. If and only if summation 2 to the k times the 2 to the kth term, right? That's the corresponding series converges, right? So what do we have here? We're going to have the n is going to be 2 to the k. We get 2 to the k log 2 to the k, applying it to p. So that converges if only if that converges. Sorry, let me just make a point back here. Sorry, regarding money and exponential function. So like the derivative of e to the x is e to the x, right? So that means that the rate of change of the speed, the velocity of your money in the bank, basically, if, you know, this is not exactly what you get, but something like this, but it means that the velocity that your money is growing is basically equal to the money that you have, right? So if you have $1 million, that means that your $1 million is growing at, that's basically the velocity of your money, right? So the less money you have, the slower it grows. The more money you have, the faster it grows, right? So basically, the moral is save a lot of money really quickly to get up into the bigger ranges, right? And then you worry less later. Yeah. So that's the moral of this, right? You learn this all the time, but there's a very, very real moral to it. Save a lot quickly. Get into the bigger ranges so that the velocity is faster. Okay. Okay. Yeah. So this converges differently. This converges, right? Of course, there's some cancellation that happens, and again, you can use your knowledge of the logarithm to say what? What do you know about the logarithm? Yes, and
You can move the k to the front.
move the k to the front. Right? So properties of log, right? So we need to k. So consider. So take this thing. We say 1 over k log 2 to the p. We have k to the p here, right? Right, that's what we're looking at this thing, right? 1 over k to the p, log 2 to the p. Log 2 to the p we can pull out, right? Because that's just a constant. 1 over log 2 to the p, summation 1 over k to the p, right? As k goes from 1 to infinity, right? And so what are we looking at? Geometric series. Right? It's just a geometric series which converges as long as p is bigger than 1. Right? Right? So converges if and only if p is bigger than 1. Okay. So I really like how Rudin lays this out. Right? He introduces the Lacunary series, he introduces the geometric series, and then he says, well, look, we can sort of bootstrap our way up from the geometric series. We can bootstrap up to the p-test, and then from there to this sort of super p-test by combining with the Lacunary series at each step. Okay. Let's get on with it. I'm going kind of slow, but close your eyes for a second. Raise a finger if this is too slow. Okay, thank you. I mean, like I can go much faster, but what's the point? Okay. Okay, root and ratio tests. So we have these tests to convergence tests, right? Convergence tests for series. Right. Do you guys remember root? You probably heard of root and ratio tests before. Yeah. So here's the first one. We'll do the root test. Okay. So it goes like this. You say, well, look, you have a series, given series, let alpha be the lim sup of the nth root of the absolute value of the nth term. This is, the one you saw back in Calc 2 is like this, without soup in it. Okay, we're going to put soup in. Then, 1, if alpha is less than 1, then you have convergence. If alpha is greater than 1, you have divergence. If alpha equals 1, then you have no information. Okay, got 7 minutes. That should be plenty of time to do this, but not the next one. Okay, so here's the idea. Okay, the idea is you say, well, look, suppose we had let me make sure. Yeah. Suppose we have that instead of that the limit of this the lim sup of this equals alpha, suppose we have this thing actually equals alpha. Okay, suppose alpha, suppose the nth root of the absolute value of the nth term actually equals alpha. Okay, in that case, a sub n is going to be alpha to the n. Right? The absolute value of a sub n is going to be literally alpha to the n, right? And if alpha is less than 1, well then, summation of alpha to the n converges, right? Summation of alpha to the n converges, which is to say that summation of the absolute values of a to the n converges. But that means that your sequence is absolutely convergent. I'm sorry, your series is absolutely convergent, and so it's going to be convergent. Okay, and similarly, right, if this thing, well, it's actually a little bit trickier, but anyway, but this is kind of the idea. Basically that, your sequence, if this sort of thing happens, then your sequence is basically a geometric series, right? Basically a geometric series, and that converges if and only if the ratio is smaller than 1. So, okay. Anyway, so that's the idea. We don't have that, of course, right? We don't have that this is equal to that. What we have is, so proof. We have that the lim sup of this thing equals alpha. Okay, so now suppose alpha is smaller than 1. Okay, here's 0, here's 1. We have an alpha smaller than 1. Okay, well, since alpha is smaller than 1, we can squeeze some number between there. Okay, choose x between alpha and 1. Okay, good. Okay, well, remember what the lim sup has. The lim sup has that sort of like half limit property, right? Lim sup has the half limit property that, we can ensure given anything bigger than the limb soup, we can ensure that everybody stays under anything that's bigger than the limb soup, right? So you take, given any epsilon, maybe think of this as alpha plus some little epsilon. Given any little epsilon, you know that there's some time past which everybody stays below the line, right? That was the limb soup property. Limb inf is the opposite property, right? So we know there exists a time such that if n is bigger than that time, then this thing is smaller than x. Right? But that's good enough, right? That's good enough because then we get that this thing is smaller than x to the n, right? And then we do the same thing. We do exactly the same thing, right? So dot, 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 that implies that summation a sub n converges. Okay. Now, let's get the not the converse, the divergence. If alpha is bigger than 1, right? If this limb soup is bigger than 1, well then, we know that there's a subsequence, n sub k, a sub n sub k, that converges to some number r bigger than 1. Right? Because the limb soup is the supremum of the subsequential limits. Right? So if that limb soup is bigger than 1, there's got to be stuff that converges to something between 1 and alpha. Okay. Right? But that tells you that this thing is going to be bigger than 1 for all k past some point. Right? But what does that tell you? That tells you that the absolute value of a sub n sub k is bigger than 1, for all past that point. Right? But then you fail to converge by the divergence theorem, right? There's an infinite number of guys, there's an infinite number of elements of your sequence that don't go to 0. Right? These guys all stay away from 0, and so your sequence cannot converge to 0, and so your series must diverge. So divergence test. Okay. The last part, to show that this thing gives you no information at all, what you do is you apply it to 1 over n and 1 over n squared. In either case, you're going to get alpha equals 1, alpha equals 1. Now this one converges and this one diverges. So you see that getting an alpha equals 1 tells you nothing about convergence divergence, right? Because this one diverges and this one converges. Okay, next time we'll continue with more clearing up of your old calculus 2 knowledge with the ratio test, with a sort of modified ratio test. And then we'll go to power series and then some really complicated stuff. So start reading the stuff from power series onwards. Yeah, because things get kind of technical after that. Yeah. Yeah, this is kind of the fun part, and then comes the awful part. And then we'll start a new chapter. There'll be like one more lecture of semi-fun stuff, And then 1 week of kind of awful stuff, and then we'll start a new chapter.
What is the next chapter?
Oh, we'll go to chapter 7, actually. Yeah. Chapter 7, sequence and series of functions. So, right, your points are not points anymore. Your points, each of those points will be a function, and you'll be talking about convergence of functions, rather.
Thank you.
Bye-bye. Bye. You're welcome. Bye.